Oh, hello, good morning. So today we will talk about the DFS depth search algorithm. So let's start. Okay. Yeah, if you have any question, please yes, drop me a message in the chat room box so that I can reply you during the temporary break. Okay, so last week we have talked about the breadth search algorithm, which is like if we start from a certain node, we want to visit all the nodes connected to the source node, so that in the order of the distance from the node. But here we will talk about a different strategy of visiting all the nodes starting from a source vertex. So this algorithm is called DFS, depth search. So the major idea here is that we will try to visit from the current position to a neighboring node if there is a way to do so. And then, so we start from a source node, go to some node, and then if there is still a way to go further, so we will still visit the node and so on and so forth until we do not find any way to move forward, so that we go back a little bit and then we will see an example, so that as long as we still find a way to go further, we will do that first. So that's why we call this depth search. We want to, it's like exploring the oil under the ground. So we go deeper and deeper and deeper until we hit some hard rock. So in that case, we go back, and then whenever we still can go further downward, we will go downward again. So if you describe the algorithm, it is best represented by using recursion. So the idea here is, so DFS, let's say it is a procedure of performing depth search starting from a certain node U. So when we perform DFS of U, we will first, say U is now discovered. And then what we are going to do next is, while U has some unvisited neighbor V, we will continue to explore V and whatever we can do starting from V. So we will perform DFS of V. So when DFS of V goes back, so that we can no longer go further, we will see whether U has still another side branch neighbor that is not visited yet. So in that case, we will perform DFS of that new neighbor and so on and so forth. Once everything is done, then we will mark U as finished. So perhaps it's better to describe everything by using an algorithm. So here in this example, we have an example graph. This is a undirected graph. And then we start from the source vertex, let's say S. So one way of doing so is, so we start from vertex S, we see whether there are still unvisited neighbor of S. If there is any one of them, we will just pick one of them to begin with. So in our example, let's pick W. So S will now pick W. So this is S discover W. And then now we are at position W here. So we will ask ourselves, is there a way for us to go further without going back? And then we see that W will still have a neighbor X, which is unvisited. So we will move to X. So in that case, W will then move to X. So we will mark this edge with a directed arrow. And after that, what should we do? If you are okay with this one, so we will ask whether X has unvisited neighbor. Yeah, in this case, S is already done. So we will undiscovered neighbor. So in that case, we will move to T. We move to T, and then T will move to U, and then U will move to V. So this is the scenario that we are here. We are now at this, U will move to Y. So this is the scenario that we have. At this moment, we will see that Y can no longer do anything, because Y do not have any unvisited neighbor or undiscovered neighbor. So in that case, we can mark Y as a finished node. So it is now done. Y is now done, so we go back. And then we will see that U here, you do not see any side branch that is still unvisited. So in that case, U is also done. So we will mark U as done. and then we go back. And here, T doesn't have any other neighbor that is unvisited. So we will mark T as done. So we go back. When we go back here, we will see that X will also check this as a neighbor, but then this one is pointing to S. S is already visited. So in that case, X do not have any existing neighbor to visit. So we will mark X as finished. And then we go back. We will mark W as finished. And we go back. Now at this moment, S is not done yet. It is because S will still have a neighbor which is still not visited. So we will continue to process Dfs of R starting from S. Okay, so S will now point to R because S discover R as an unvisited neighbor, and then we are going to explore whatever we can do about this R. R will then discover V, and then we cannot do anything, so we will be done. R discover V, we cannot do anything further, so we will be done. And then after that, we go back to R. R doesn't have any other neighbor to visit, so R will be done. And then we go back S, and then S here, at this moment, it has all the neighbors traveled. So in that case, S is done as well. So in that case, this is the whole process. When the whole process is done, yeah, we can also see that by keeping all the directed edges that we are using during the algorithm, this should form a tree rooted at S. Yeah, because we can see that everything will be linked to S eventually, and then every node will have exactly one arrow pointing into it, except the root node, of course. Okay, so every node will have exactly one arrow pointing into it. It is from the node that discovered it. So in that case, we will have a directed graph, and then it is actually a rooted graph, rooted at S. And we call this graph a DFS tree, okay, of S. Now notice that the DFS tree of S is not unique. So it really depends on the process of this DFS algorithm. So if at the beginning we start picking X instead of W, then we will have a different DFS tree, because in that case we will have S discovering X, X discovering T and U and Y, and then X will be the one who discovered W instead of S. So in that case, we will have a different DFS tree of S. So DFS tree of S is not unique, and then it is obtained by really running a DFS algorithm. So it depends on the choice of which neighbor to visit during the running of the algorithm to determine the shape of the tree. So let me check. So let me quickly check if you're okay with everything so far. So far, okay. Okay, so let me continue. Okay, now, so BFS or DFS has a problem. So it may not visit all the vertices of the input graph for two reasons. Okay, the first one is the graph G may be a disconnected graph. So the graph G may have more than one connected components. So in such a case, if we start from S, what we can do here is that we can only visit those vertices that are reachable from S. So all those nodes that are not reachable from S, we will not be visiting them. And then the other case is the graph G itself may be directed. So again, in a directed graph, although things look like they are in the same component, but then if there is no directed graph and directed path from S to the node, then we will not be visiting them. We will see an example soon. But then usually in most application of the DFS of BFS, we will run DFS on a certain source node until we do not have any further node to discover. And then if the graph still has some remaining node, we will continue to run DFS on some unvisited node as the source until everything is done. Okay, until everything is visited. So this is the usual case of the application of a DFS. So for instance, let's look at this example. This example graph, originally it is a directed graph. Okay, so it is a directed graph. And then let's say we start from S. Now, as we can see, because the edges has arrows, if we start from S, there's no way that we can go to R because there's no directed path from S to R, right? So as we can expect, after running the DFS starting from S, we will see that R cannot be visited. So let's see what will happen. Okay, so if we start it, so before we move on to the next page, let's do some checking with our brain. Yeah, here. So what will DFS do? So if we start from S, then there is only neighbor that is connected from S. So S will then visit W, and W will visit X. Now for X will see that there is an arrow here, but then it is pointing to something that is already visited. So, and then X doesn't have any other neighbor to go. So in that case, X will be done, go back, W will be done, go back, and then here S, you don't have any new neighbors to visit, so S will be done. So after the first process of DFS on S, these are the exact nodes, exactly 3 nodes will be discovered and visited. And then we have, okay, so we have this arrow, this is the arrow of discovery. And although there is a pointed arrow originally in the graph, then this arrow is not the one that is for discovery. So we will mark it as a dotted arrow. Is that okay? And so in most algorithms, so when we apply DFS and then we see that it is not visiting every node here so far, so we will continue to apply the process on some unvisited node as the source. So here, let's pick T as the source. So if T is now a source node, then what will happen is T will discover U, and then we will get something like this. But then we will also see from T that there is a neighbor X, but that X is already visited already. So we will mark this as a dotted arrow. Okay, so for this graph, there are still unvisited nodes. So what we are going to do here is that we pick one, any one of them, and then we will try to run DFS on it. So let's pick Y. So this is the case after running DFS on Y at this moment. And then let's pick perhaps R, and then we will have this. And then finally, we pick V. Yeah, we will have this one. So at this moment, all the nodes are visited. Then we are done. And again, in this case, we will still have a DFS forest. So the DFS forest keeps exactly those edges of which node discover which node. Okay, so we will have S discover W, W discover X, and then X doesn't discover any new node, so we will have this one. T discover U, and then for all the others, they are isolated vertices. So here, they are not discovering any new node. So this is a DFS forest because each one of them is a DFS tree. This is a DFS tree starting from S. This is a DFS tree starting from T after we have processed DFS on S. And then these are the DFS of Y, R, V after we have processed the previous nodes. Okay. Now, if we look at the complexity, so here this algorithm actually we are just applying what? Yeah, we are just applying this very simple function, so you can write DFS very easily. So how do we compute or analyze the running time of the algorithm? So the idea is very simple. So first of all, we will see that no vertex is discovered twice, and then each edge is visited or is seen at most 2 times. So for a particular edge, let's say we go back to the original graph. Let's say this is the original graph. Let's say this edge. This edge is seen only when we are trying to run DFS on S. Then we will see this one, and then for no other time we will be seeing this one. So in the directed case, each edge is seen exactly once. But in the former undirected case, so this is the undirected case. So let's say this edge. So this edge will be seen when we are trying to run DFS on S, and then later we move to W, we run DFS on W. from S to W, we will see that this edge is discovered. It's representing how S is discovering W. But when we are at W next time, we will look at this edge again, but then we will see that this edge is already been used, so we will just forget it. But then notice that there are no other time we are going to see this edge again, because when we are at X, we will only see all the edges connected to X, so we will not see this edge again. So every edge in the undirected case is seen exactly 2 times. So the total running time, therefore, is order of V plus E. And then for DFS, the best way to run it is to use the recursion, but then we can also perform DFS by using a stack. So you can check easily from the web how to run DFS on a stack. So actually recursion, if you study operating system or programming language or some other courses later, then you will see that what we are really doing using a recursion is we are using a stack provided by the operating system to help us to perform this recursion. So when DFS is implemented using the recursion, then we are using the stack from the system. On the other hand, we can also write our own stack so that we can perform DFS using our own stack instead. So there are 2 different ways. One is using the system stack, one is using our own stack to implement the DFS algorithm. Okay. And then one question, we want to know a little bit more about the properties of the DFS. So here in this example, so we will see that, okay, S, W, X are in the same tree, T and U are in the same tree, Y will be an isolated vertex, and so on and so forth. So how can we decide which nodes will be on the same tree? So at the beginning, so if we run DFS on S, how can we determine that W and X will be on the same tree? And by the time when we are starting to run DFS on T, how do we determine that what will be in the same tree as T? So it really depends on the ordering, right? So if we start instead, if we do not start from S, if we start from T originally, who will be in the same tree as T? So we will see that T will discover U, go back, T will discover X, X will discover S, S will discover W, go back, go back, go back, and done. So if we start from T originally, then we will see that T, U, X, S, W, they are all in the same tree. But if we start from S originally, we will see that only S, W, X in the same tree, and then T, U will be in a different tree. So how do we know who will be in the same tree? Okay, so here we will introduce something called the white path theorem, and then it is exactly the theorem that determines who will be in the same tree by the time, who will be in the same tree as V by the time we perform DFS on V. Okay, so the white path theorem is very simple. So perhaps we can talk about the white path theorem first. Okay, let me see. Okay, so let me see how can I talk about the white path theorem. Okay, so we can go back to the previous example. Okay, so the white path theorem is very easy to understand. So at the beginning, all the nodes are white because it doesn't have any colors on it. Okay, so the theorem says that if we are running DFS on a certain vertex, let's say S, when we run it, who will be in the same tree as S? It will contain those nodes that are reachable from S using only white nodes. So in that case, W will be in the same tree as S, and then X will also be in the same tree as S because X can be reached from S by using white nodes only. Is that okay? So let's say this is the case. And now let me ask you a question. So if we now run DFS on T, who will be in the same tree on T at this moment? Then we will see that U will be a node that is connected to T using only white paths, only white nodes, and then Y is not reachable. Now X, although it is reachable from T, but then X is already marked as colored. And similarly, S can reach from T by using this way, right? But then the way that you reach from T is you are using a mark node. So in such a case, then we will see that S will not be in the same tree as T as well. So W will not be, X will not be. So the only case is T and U. Is that okay? So this is the so-called white path theorem. Okay. And to prove why the white path theorem, so the white path theorem is strong, it says that any node, okay, so we will talk about it soon, but then the idea here is that any node reachable from V by the time that DFS is run on V using white nodes will be in the same tree. And these are exactly those nodes that are on the same tree. So no more and no fewer. Okay, but then before we talk about the proof or whatever, let us also talk about something related to the DFS algorithm. So when we are running the DFS algorithm, we can somehow record the relative time that we are discovering a node and finishing a node. So these are called the discovery time and the finishing time. And then we will see that for any node, the discovery time must be earlier than its finishing time. Okay. And to illustrate what I want to say, so let's run this example. This example is our first example that we run DFS on as undirected graph. Okay, so what happens is S discover W, W discover X, X discover T, T discover U, U discover Y, and then Y doesn't have anything to do. Y goes back, U goes back, T goes back, X goes back, W goes back, and then S still has a neighbor. S goes to R, R goes to V, V goes back, R goes back, and then finally we find that S is now finishing the process. Is that okay? So this is how we were doing the DFS of the undirected case in our first example. So in that case, we can use two numbers, one to represent the discovery time and one to represent the finishing time of a node. So at time 1, we are at S. So by the way, the time is not that very strict. So we just need to find out the relative order. That's what we need. So let's call it 1. And at time 2, we are here. And then time 3, time 4, time 5, time 6, we are here. And then we try to go back. So let's call it time 7. Time 7 finds out that it is finishing. So this is the time that it finishes, so that it goes back. And then we discover that this is now finishing. So it is time 8. We go back. Time 9, we go back. Time 10, we go back. Time 11, we go back. Okay, although we can say that it is at time 12 that we move to here then, but that's okay. We just need the relative order. So we can say that, oh, at time 12, we are discovering this node. 13, and then 14 finishing, 15 finishing, and 16 finishing. Okay, so we want to have the relative time for the discovery and the finishing of every node. And then we hope that all the numbers here are not the same. They are all distinct. And then there is a interesting, okay, so this is another example. This example corresponds to the case of the directed case. Okay, so in the directed case, the running, let us recall, it is from S to W to X, goes back. So we will have 1, 2, 3, 4, 5, 6. And after that, we have tried to start the remaining process by running DFS on T. So at time 7, we are here. Time 8, we are here. Time 9, we are finishing. Time 10, we are finishing here. So this is 7, 8, 9, 10. Okay. And then next 11, 12. And then next 13, 14. And then next 15, 16. Is that okay? And then we have an interesting observation. So first of all, for any node, the discovery time must be less than the finishing time. Yeah, you must be discovered before you can finish, right? And then the next one, yeah, we try to do what? We try to make sure that every relative timing is distinct from each other. So du, dv, fu, fv, they are all distinct. And then the most interesting case is this so-called parenthesis theorem. So, the parenthesis theorem looks like this. So for instance, if you look at this, you can think of this as a time interval starting from time 1, ending at time 6. So it has all the intervals representing the numbers 1, 2, 3, 4, 5, 6. So this is an interval from 1 to 6. And let's say this is the interval from 7 to 10. Now we will see that these two intervals, they do not have any overlapping. So this is one of the cases that two intervals could be, they do not have any overlapping. But another case is, let's say these two, they are actually overlapping, 1 to 6, and then this is 2 to 5. But then we will find that when they overlap, one must be properly containing the other one. Okay, so 1, 6 is very long, and 2, 5 is totally contained between 1, 6. So in that case, this is the so-called parenthesis property. So it's like when we are trying to write a sequence of balanced parentheses, the first parenthesis and its matching defines a certain interval, and then another open parenthesis with its corresponding closing defines another interval. We will see that the parenthesis interval, they are either disjoint. So disjoint, this is the case. Second case, we call it disjoint because we will have du, fu. This is all about the interval of u put in the front, and then this is the interval about v, and then the whole interval of u will appear before the whole interval of v. Okay, so this is called the disjoint case. They don't have any overlapping. Or the other case is containment. So we will see that the whole interval of u is from du to fu, while the whole interval of v is from dv up to fv. So we will see that du and fu will contain the middle interval properly. Yeah, containing. So here, this is the case. Yeah. The idea of proving this is not difficult. Okay. So first of all, so let's look at this example. So this example, you will see, 116, okay, is containing everything. It is because this is the source node, right? So source node is the one that is starting at the earliest time and then finishing at the last time. So this is like the whole interval that is containing everyone. Indeed, we can see that if one node discover another node, so this node discover this node, right? The first node has an interval containing the second node. It is because the first node discovered the second node, so that this has earlier discovery time. But on the other hand, because this one is the one that is discovering the other one, we have to wait this to finish the DFS search before we can finish this node. So in such a case, this node, the first node, must have a later finishing time. So if you see directed arrow, it means that for each directed arrow, so let's say this is a directed arrow, it means that the one pointing to the other will have a longer interval, properly containing the one that is being discovered. And now, if two nodes do not have any way from one joining to the other, so these two nodes are completely not related, then we must be able to see that the interval of this one and the interval of this one could not have any overlapping. Okay. Yeah, because if there is overlapping, then we have a contradiction. So for instance, let's say this is from 4 to 9, and let's say this is something like from 5 to something. Then we will see that this is from 4, but then this is from 5. That means that we have to finish this one before we can finish this one. So in that case, this should have a longer finishing time rather than disjoint. Okay, so this is a nice, very nice property about the discovery time and the finishing time of a DFS search scenario. Okay, so let's see. Let me check briefly if you are okay. Okay, thanks. What does VE? Sorry. So V here means that the vertex set, and then E here means that the edge set. So size of V means that how many vertices are there in the graph, and the size of E means that how many edges are there in the graph. Okay, so okay, so how about BFS? So BFS is like, so what is BFS? BFS is we start from a certain, okay, so we can use a certain graph as our example. So BFS is a different searching algorithm. So let's take a look of this case. Okay, so BFS will do what? So we start from a certain node. We will next visit all the step 1 node from away from it. So from S, we will visit R, W, and X. After that, after this big batch of processing, we will try to visit all the step 2 nodes from S. So we will next visit V and T. And after that, we will visit the step 3 nodes. So we will visit U, and then finally we will visit Y. Is that okay? So if we start from S, the process that we are going to visit will be something like R, W, X. Is that okay? And then V, T, and then U, and then Y. So BFS will work out like this. So it is completely different from the DFS. So you will see another big difference from BFS and DFS is, for BFS, we will have jumping. So after we have visited RWX, we can then visit V, and then we can visit T. So we can jump from V and then next from T, right? But then for DFS, it's interesting. So DFS is like we are always walking along the edges connecting to the nodes to each other. We go back, go back, go back, go back, go back, something like this. Is that okay? So the DFS process is very useful in like you try to write a program to guide how a mouse can escape a maze. So when you do so, then the finding the best way for a mouse to escape the maze is usually using DFS, because we can ensure that each step it is really you are going to the neighbor. But then DFS has a weak point. Okay, it has a weak point because we have lost information about how far away from the current node from the source node. So for instance, although X is very close to S, we are not visiting X from S directly. We are visiting X via W. Is that okay? So in such a case, we don't know how far X is really away from S, except that we know that X is reachable from S. So this is a weakness of a DFS algorithm. Okay. So let me see if okay, good. Okay, good. Okay, so let's continue. Okay, so now, okay, so we have done with the discovery time and finishing time. And then we will come back and see this again. Yeah, proof of parenthesis is just what I've just presented, and then here this is a corollary. So here, so we have seen that if a node is discovering another node, the first node is discovering the second node, the interval of the first node will be containing the second one. So inductively, if in the DFS tree, one node is the ancestor, so one node is the ancestor and one node is the descendant, then we will also find that the ancestor will have an interval properly containing the descendant's interval. Yeah, because this contains this contains this, so that this one contains this one. Is that okay? So you can prove this corollary like this. Okay. And then, okay, so we are now with the white path theorem. Actually, the proof of the white path theorem, we can do so using a tedious proof that we are presenting in the lecture notes. But then we can also think about this intuitively, why this must be true. So first of all, so here, this is like, so here, this, let me recall this. This is a very strong theorem. It says that whoever can be reached using white nodes only will be the descendant of S in the DFS tree. And then every node, so this is like okay, let me recall. Okay, so first of all, who will be visited? So they must be the white nodes connected. So they must be connected by white nodes from the current node. Okay, and then on the other hand, we have the converse. So any node connected using the white nodes path must be visited. Okay, so this is like if and only if this is like the exactly case. So let's try to prove, or let's try to see why this is correct. So first of all, if two nodes are connected by a white path, so for instance, S can reach U using a white path, then we claim that by running DFS on S, we must be visiting U before we finish S. So that means that U will be a descendant of S. So we can prove this by contradiction. Okay. Now suppose that U is not visited during the DFS on S. Okay. Or if there is some node, okay, that is a white node connected by using white nodes, sorry, that is white, and connected by a white node path, then suppose that it is not visited, then we will say there is something wrong. Now, the reason is that, okay, if such a node exists, we can find one that is closest to the source node. So the closest means that we can find one such that all the neighbors are not white. If there is a neighbor which is white, then we will pick that one. So in the end, so in that case, so first of all, S must be visited in the end. Is that okay? So there must be some node that will be visited by S through the algorithm, and then some node which is not visited. So in such a case, there must be a certain node. So you can think of this as the graph is having some marked part and some white part. So there must be a certain boundary between a certain white node and a certain marked node. So in such a case, so for instance, S will be visiting W and X, but somehow, for some strange reason, it doesn't visit U. So in that case, U is still a white node, but then its neighbor from U to S, okay, is already marked. But then this doesn't make sense. It is because by the time that X is a marked node, that means that X has finished visiting all the neighbors. But then U is still a neighbor that is unvisited. So this is not making sense. So in such a case, a contradiction occurs. So in that case, we cannot have a node which is still white, but then it is originally connected to the original source using white nodes only. Okay, so we are now, first of all, done with one part. As long as a node is connected to the source by white nodes, then it must be visited. Okay, then we want to prove the other direction. The other direction is, okay, so let's make sure that we are on the same thinking process. So make sure that we are correct. So the first one claims that if it is white and then connected, then it is visited. The other should be, if it is visited, it must be connected by white paths. Yeah, but then if it is visited, then that means that we must have a way of discovery from this node to another node, this node to another node, this node to another node. But then we will find that this discovery process can only visit white nodes. So in such a case, if a node is discovered, then it means that it is connected by a white path. Okay, so let me write down, perhaps, so that we want to make sure that we are on the same track. So let me type things here. We want to show this one. Okay, 1. Add water and dual on Valorant. Okay, so sorry, let me type. Okay, so the first one is if source S is connected to U by weight path, then U is visited during Dfs of S. Oh, so this is the first one, and then we have the second claim. If U is visited during Dfs on S, then S is connected to U by a weight path. Okay, so if you can see, then these two are like if and only if. So it defines exactly what are the nodes that are really visited by S during the DFS of S. So this is the so-called weight path theorem. The first one is we can show this by contradiction. And then the second one, we are showing this by simulation. So we simulate the process, how U is visited during the DFS of S. So it must be through a certain weight path. Okay, so actually, this is all what I want to talk about DFS originally. Okay, but then we still have plenty of time. So let me still bombard you with something else. So we are done with actually lecture 23, but then we still have time. So let's try to look at something a little bit more. So we go to lecture 24. Okay, so lecture 24 is a very nice example of application of the DFS algorithm. Okay, so lecture 24, we will talk about an algorithm for solving a problem called topological sort. So it is a kind of a sorting algorithm, sorting the vertices of a graph according to the shape. But then, since we have just mentioned about DFS search, so let's look at a little bit more about the edges of a graph corresponding to a DFS search. Okay. Now, during the DFS process, we are going to classify the edges of a graph into 4 types. So we still remember that after the running of the DFS algorithm, we will have a DFS forest. So all the edges on the DFS forest, we call them tree edge. So there are 3 edges. And then there are some edge, we call it back edge. So we will see what is meant by back edge, and then we will see what is meant by forward edge, and then we will see what is meant by cross edge. Okay? So they are easy to understand concept. So let's take a look. Okay. Consider this input graph. This input graph is a directed graph. So let's simulate a DFS algorithm on it. So perhaps using this graph, DFS would try to go to R to S, and then perhaps, I don't know, S could go to W or X, depending, maybe S to W, W to X. So this is one part, and then T to U, Y, and then V, something like this. Yeah, so this is like R to S, S to W, W to X, and then T to U, and then Y, and then V. Is that okay? Now, the solid edges are the 3 edges because these solid edges are those that are appearing in the DFS forest. And now we can talk about the remaining edges. So they are not appearing in the DFS forest, but then still we can give them some name. Okay, so first of all, what is a back edge? Back edge is pointing from some node in a tree. So this is, there are a couple of trees. So the green tree, the red tree, the orange tree, and the purple tree, right? So what is a back edge? Back edge is an arrow pointing from a node in a certain tree back to some of its ancestor. So whenever you see a back edge, that means that there is a certain cycle going on. So R to S, S to W, W to some ancestor. Could be R, could be S, whatever. So there is a back edge. Now, so back edge is pointing from a tree node to another tree node, but then they have ancestor relationship, ancestor descendant. Okay. And then we can also talk about forward edge. Forward edge is the opposite. We are pointing from some node to its descendant, but they are pointing by using not the tree edge. Okay. And then we can have cross edge. Cross edge are those that are neither the backward edge or the forward edge. So these are the cross edge. So cross edge could have two cases that we can have. One is we are pointing from a node in one tree to another node in another tree. So this could be a cross edge. But then you may have, let me see, this is what I guess. Can we have cross edge within the same tree? Let me see. No, we can't. Okay, so in that case, yeah, cross edge is those edges, not three edges, and then not backward and not forward. So if you're okay with this, yes, let me double check if everyone is okay. Okay, good. Okay. Okay, so we now have a classification of edge. So here in this example, we are starting with a directed graph, and then we can see that there are all kinds of edges could be possible. We may have three edge, and then backward, and then forward, and then cross. Okay. Now notice that this is a different way of doing the DFS. So it could be like R to S, S to W, S to X first. Okay, so this is the other way of doing DFS. R to S, S to X first, but then X cannot go further, so we go back and then S to W. In such a case, then we will see that we don't have, this is not a forward edge because W and X doesn't have any ancestor and descendant relationship. So it is not forward, it is not backward, and then we call it a cross edge. Is that okay? So there are two types of cross edge. One is you can point within the same tree, and then you can point across different trees. Okay? Now, if the input graph is undirected, what will happen? Now you will see that it's really interesting. This is undirected. For an undirected graph, we can never have forward edge, and we can never have cross edge. Okay. So for an undirected graph, the DFS search will only give us two types of edges. One is the tree edge, and all the others, they must be backward edge. So this can be proven by contradiction. So if there is a forward edge, then why do we have a forward edge? So this edge should considered as backward, right? Because when you have time, so for instance, if this is a forward edge, then why should it be forward? Because when we consider this one, this is already here, so it looks like it goes backward, right? And then we can't have cross edge. If undirected DFS, undirected graph, it has a cross edge, then yeah, you can think about this yourself. Okay, so you can see that whenever you see something, we call it a cross edge, then that means that you are not doing the DFS search properly. So think about this at home. So this is a good exercise for you to understand everything. So let me recap. Okay, in directed graph, all edges are possible, but in undirected graph, you just have two types, either tree edge or back edges. Okay. Okay. And then there is also a theorem. Okay, if we run DFS on a directed graph, and if there is a back edge, then that means that G must have a cycle. So obviously it is true, right? But on the other hand, if G has a cycle, then you must be able to find out a certain back edge in the directed graph. So for instance, let me see if we have an example with a cycle here. So we have a cycle here, right? So it says that if you have a cycle, in any case that you run this algorithm, you must discover a back edge. On the other hand, if a graph has a back edge, there must be a cycle. So one direction is easy, the other is not difficult. Okay, so the easy one is if it has a back edge, then it completes a cycle. So back edge implies a cycle is easy. Now, how about the other case? Now, if G has a cycle, let's call it C. So there must be some node that is first visited in the DFS algorithm. So let's say V is the first one that is discovered in the DFS algorithm. But then in that case, using the what? Using the white path theorem, we will see that if when we complete the cycle, let's say U is the node that is pointing to V, okay, that completes the cycle, then in that case, U will be a descendant of V in this DFS forest using the white path theorem because V is the first node in the cycle. So all the cycle nodes, they are all white. So we can join to the node U that points back to V to complete the cycle by using white path. So in such a case, U will be a descendant of V, and in that case, the edge pointing from U to V will be a back edge. So this is the good thing about the white path theorem that we can apply immediately. Okay, and then yeah, so please give me some time so that I can finish this topological sort, and then we can have an early lunch break. Okay. Okay. So let me double check if you have any questions so far. Okay, good, excellent. Okay. So okay. So today we are really doing something nice. We are really ahead of our schedule. We can finish 2 lectures in one time slot. Okay. So what is the topological sort problem? So here we have the input, which is a directed graph, and then the arrows on the graph may represent, so each node here may represent a certain task that we need to do, and then the arrows represent the dependency. So we must finish something of a node before we can finish something of another node pointed to it by the arrow. So let's say we have this example, we have this graph representing the process of wearing. So in normal case, we should be wearing undershorts before we wear the pants, and then we should wear the pants before we put on the belt. And similarly, we should normally, wear the pants before we have the shoes, and we should have socks before the shoes. But then there are no dependency between the pants and the socks. It's okay, you can wear the socks first and then wear the pants, or wear the pants first and the socks, and so on and so forth. And then wearing the watch can be done at any time, so there is no dependency. And then shirt and tie. So of course, you should put on the shirts before you can put on the tie. Okay. So we have a bunch of tasks that we want to finish, and then we want to find a way so that we can do the jobs one by one without any problem. So that we want to make sure that by the time that we need to do a certain job, let's say tie, all the things that it depends on that should be done earlier by it is already done. Okay. So in that sense, what we are trying to do here is we are trying to arrange the nodes from left to right so that all the arrows are pointing from left to right. Is that okay? So we want to list the nodes one by one from left to right so that all the arrows are pointing from some node from the left to some node on the right. You don't have backward arrow, okay? In such a case, then we can process the nodes one by one, starting from left to right, and so that there is no problem. Now for this problem to make sense, the directed graph should not have a cycle. There should not be a directed cycle, because in that case, there is no way to arrange the jobs so that we can do so one by one without one depending on the other. Okay. So we call this graph a precedence graph. What things should precede? What things should be done before another thing? So this is so-called precedence graph. So we have given a precedence graph. We want to order the events such that if UV is an edge in the graph, then U appears before V in the ordering. And then this problem is a kind of a sorting, right? So we are sorting, arranging the nodes into some order. But then this is not about the value of a node, but this is about the shape, who points to who. So that's why we call this a topological sorting. Topological means that it is talking about the shape of a graph. And then this is what we have done. If a graph contains a cycle, there's no way to have an ordering. And now, let's see. There are two major ways to solve topological sort. One is by using a queue. Let's make it into an exercise for you. But then the other way here is we can apply DFS. So we will talk about this way today. Now, so to apply DFS on a graph G, so we can start with any node and then do DFS, and then if there are still remaining nodes that is unvisited, we continue to do DFS, and so on and so forth. Now we have done with directed graph. If G contains a back edge during the process, we will see that there is already a directed cycle, so we can abort the sorting because no one can sort the vertices properly. But on the other hand, then what we are going to do here is that we are going to output the vertices in decreasing order of their finishing time. So whoever finishes later is the one that should be put as the leftmost vertex. And who finishes the second latest will be the second leftmost vertex, and so on and so forth. So let's see if we have a running. Yeah, let's check of the running of this algorithm. Okay. So this is the algorithm, very simple. Basically, you just run DFS once. Okay, and then we are done. Okay. So let's see this example first. Okay. So we run DFS. For instance, let's try to run from shirt. Time 1, time 2, time 3, and then we go back time 4, time 5. And then here, we still do not finish because there's still an arrow. So time 6, time 7, time 8. So 1, 2, 3, 4, 5, 6, 7, 8 is here. And then at time 9, we are here. Time 10 here. And then 11, 12, 13, 14. So we are done. 15, 16, 17, 18. So we are done. So this is one example of the topological sort. And then we claim that what we are going to do, we are going to find out whoever has the last finishing time, so this one. And then we should put it at the first job. And then the second last, this is the second job. And then who is next? Socks, because 14 is a very large number. This is the third one. This is the fourth one. And then next, fifth. And then what else? And then shirts. And then belt, and then tie, and then jacket. So this is how, after running this DFS on this directed graph, we have the finishing time, and then we are going to output things according to the finishing time in decreasing order. Okay, so why does it work? So first of all, we assume that there is no back edge, because if there is one, then we will abort it correctly. Now, if there is no back edge, then what does that mean? Okay, then we can look at each directed edge. We want to find out that, we want to make sure that according to the finishing time, each directed edge is always from someone with a larger finishing time to a smaller finishing time. But that's trivial, right? Because in this okay, it's not that trivial because they may not be 3 edges. Okay. Now there are 2 cases. So when it is a 3 edge, okay. So we don't need to consider 2 cases. We just need to consider who, okay, what is, so for each directed edge, so we are going to examine this one. So we are examining what is the interval between this one and this one. Okay. So here, first of all, there are 2 cases. Either this interval is properly containing this interval, because this is the first case. If this is the case, then this must have a larger ending time. So this is done. Is that okay? And then the second case is, how about, for instance, this one, another type of arrow, like this one. This is another type of arrow. This is another type of arrow. From pants to shoes, it is another type of arrow. So here, what does that mean? So here, so this is like an interval not overlapping with this interval. Now for these 2 intervals not overlapping, but there is an edge from this node to this node. There is only one case that can happen. It must be the case that we are done with the DFS on this node before we are really starting the DFS on this node. This is the only case, because otherwise, this one will be an ancestor, this one will be a descendant. Is that okay? So if the two interval of a directed edge, okay, so if we see a certain directed edge, if the first node interval and the second node's interval do not overlap, it must be the case that the second interval is completely ahead of the first node's interval. Okay? Otherwise, this one will be the ancestor, this one will be the descendant. So this one will be overlapping, not disjoint. Now here, these two are disjoint. That means that this one has DFS completely ahead of this one. And in such a case, this one must have a larger finishing time. So we again will see that all the arrows are pointing from a larger finishing time to a smaller finishing time. So that's why if we run the DFS algorithm, we just need to make sure that we output the nodes according to the finishing time. Whoever is larger should be put earlier. Okay, so let me double check if you are all okay with this part. So far so good, no problem. Okay, and now, so it looks like it's like we're done, right? So we know how to do this. We know how to do this. And then how about the finishing time? So do we need to maintain a certain global clock so that we know what is the finishing time of all the nodes? And then after that, we have all the nodes, and then we need to sort, okay, the nodes based on the finishing time. It looks like we need to do so because we need to output the things in decreasing order of finishing time. But then we can really skip this part. We just need to have a stack to help us. Okay, clever method. This is what we do. That we use an extra stack to help. So whenever DFS algorithm finishes a certain node, we put it onto the stack. So in that case, the stack will be full of the nodes, and then the first one in the stack will be the one that has the earliest finishing time, and then the second earliest finishing time, and so on and so forth. That means that the things that we push into the stack will be pushed according to the finishing time in increasing order. So once we have processed the whole algorithm, all the nodes will be on the stack, and then we can output the nodes on the stack one by one. So in that case, we can avoid maintaining a global clock talking about what is the current time, and then we can also avoid the sorting of the nodes based on the finishing time, because just the stack will help us do what we want. So in the end, the total time is, we use linear time. So it is linear to the number of vertices and the number of edges to perform DFS. And then we don't need to do sorting. So this part is not needed. We don't need this one. And then we just need another linear time because each vertex is put onto the stack once and popped out once. So there's order V time for pushing the vertices and popping out the vertices from the stack. So this clever method can process the second step in order V time. So in total, it is order V plus E. Okay, so that's all for the topological sort. This is not the only way of doing topological sort. There is another way, completely different, that performs topological sort, and it also makes sense. But then we are introducing this algorithm here because this algorithm can be extended to solve a more complicated problem. We will talk about this next time. Okay, so yeah, that's all for today. So are there any questions? Yeah, if not, then yeah, thanks so much. Yeah, so I've been talking about like more than 1 hour so that you don't have a break. But then yeah, thanks a lot for coming. And then on Friday, perhaps, yeah, on Friday we will move on to either to a new topic or we are going to talk about our exam solutions. Okay, so perhaps on the next topic. Okay, thanks all for coming again. And then see you next time. See you on Friday. Yeah, thanks so much. Okay. Okay. Thanks. Okay, bye-bye.